The complements are used to deal with signed bits, allowing us to find the opposite sign of the bit which we are working with. There are two types of complements for each base, let's say R system, radix. The first one is a diminished radix complement. Okay, and then the radix complement, the second one. The first one is referred as R minus 1's complement, while the second one we refer to it as R's complement for radix R. When the value of the base R, look here, is substituted in the names, the two types are referred as, we will see, as the 2's complement and then 1's complement for the binary numbers. And the 10's and the 9's complement can be also obtained for decimal numbers. Since our interest now is in binary numbers and then operations, we will deal with only 1's or 2's complement. Okay? Why we are interested in complements? Look, the subtraction will be easy for signed bits if we use the complement techniques. In particular, by doing addition, we can achieve the subtraction by adding the complement of the subtrahend. We will see that shortly, right? And if the result is negative, then we can take its two complement. Let's take a look at 1's complement. Given, let's say, a number in binary having, let's say, n digits, right, in radix 2, base 2, the 1's complement of n is defined as follows. Let me write it down here. So 2 to the n minus 1 minus n. So this is a formula for defining the 1's complement. 2 to the n minus 1 and then 1. Here 2 to the n is represented by a number that consists of a 1, let's say, followed by zeros. And 2 to the 1 is 2 to the n minus 1 is a binary number represented by, let's say, n 1's. For example, here we can see n, okay, is number of digits, is equal to 8 number of bits, 8 bit, base 2, 8 digits, right? And then first we need to obtain the R, okay, raised to the n minus 1, which is equal to 256 minus 1, which is 255, right? It is obtained in base 10. This is a decimal number. So if you convert it to binary representation, we will have, okay, a binary number that consists of 1's only, 1's, right? All 1's. Then once we have this term here, right, minus n, right? Next step is to obtain the 1's complement of the following, okay, digit, then binary number. Then what we do is we subtract these from the minimum, so 2 to the n minus 1, right? And we obtain the 1's complement in this way. So we can also observe that, right, this factor, 2 to the n minus 1, consists of all 1's. And then 1 minus 1 is 0, and then 1 minus 0 is 1, right? Well, if you compare these, okay, these 1's complement, okay, to the original binary number, we see some relationship here, which is obtained by inverting or complementing each individual bit, right? So complementing each individual bit, bitwise invert. So if you compare this 1 will change to 0, 1, 0, 0 to 1, 1, right? And all this. So basically, 1's complement is obtained by inverting the binary number. Also, we can also use this number, right? Look, if you have n is equal to 4, then we will have a different decimal number, right? If we are dealing with 4, but still consisting of 1's, and then we can apply same rules. Get this term first, and then subtract your binary number. Now, let's take a look at the 2's complement example. So 2's complement is very similar to 1's complement, as its first step for conversion is the same. We invert, we just flip all the bits, right? However, we must add 1 to the bit as a second step, right? This is the correct way to find the signed value of a bit. And it is the form that signed bit actually take. Well, let's take a look at the following example. So here we have r, okay, again, equal to 2, and this is our binary number, and we want to get the 2's complement. The formula for getting this 2's complement is r, right, to the n minus n. Actually, this one is a radix, right, small r, right? So this is the formula for getting the 2's complement. So r to, this is our n, right? R to the n is equal here. So it is equal to 256. If we obtain this decimal and represent it in binary, then we have the following, right, binary representation. And minus n, okay, this is our binary number. And 2's complement of this is then obtained by subtracting, okay, r to the n minus our minimum n. Then if we perform subtraction, okay, we have to borrow, right, and then we obtain the following result. So actually, as I just said, the result here which is obtained is basically 1's complement plus 1. Okay, so it is easier to perform this complementation. So okay, so how? So 1's complement, we said, is obtained by simply inverting, right? 0, 1, 1, 1, 0, 0, 1, 1. So 1's complement is basically inverting all these bits. Okay, well, this is 1's complement, and in order to get the 2's complement, we add just 1. 1, 0, 1, 1, 0, 0, 0, 1, which is equivalent to the following. We just reviewed that the 2's complement of a binary number is 1 added to the 1's complement of the binary number. There is another way of obtaining 2's complement, as shown here, alternative 2's complement method. For instance, given n-bit binary number, okay, n-bit binary number, beginning at the least significant bit and then proceeding upward. So alternative method consists of the following steps. First, copy all least significant zeros. Copy the first one after copying the zeros, and then complement all bits afterwards. Thereafter, to the left direction. Okay, so here's the example. So here we have 8-bit binary number. We want to get the 2's complement. So first we copy all the zeros. So we have here 2 zeros, right? 0, 0. And then we copy the first one that appears after zeros. Okay, and then we will have 0, 0, 1, 3-bit. Okay, underlined bits. Then complement all bits thereafter means we complement all the bits after these 3 bits to the left. Okay, so we complement all these 0, 1, 0, 0, 1. Okay, all these, let me write it down. All these are complemented, which is equal to basically inverted, right, version. So 0 changed to 1, 1 changed to 0, okay, 0, 0, 1, 1, and Well, this is the fastest or another way of obtaining 2's complement in addition to the one we discussed. And this is equivalent to obtaining 2's complement via, let's say, 1's complement and adding 1. Earlier in the previous slides, we wanted to simplify hardware by sharing adder and subtractor logic, right? After we learned complement techniques, we are ready to define a binary subtraction procedure that uses addition, okay, and then the corresponding complement logic. So the main idea is here we perform subtraction using addition and then complement techniques. Well, in this example, it's a subtraction of two, let's say, n-digit unsigned numbers, m, and then n, in binary can be done as follows. First, we add the 2's complement of the subtrahend n to the minuend m. This performs the following operation, right? m plus 2 to the n minus n equal to m minus n plus 2 to the n. So here we have two possible cases. First case is m is greater or equal to the n. Right? In this case, the sum will produce an n carry, let's say in binary 2 to the n. We can discard the n carry and then leave the, let's say, m minus n as a result. Well, if m, minuend, is less than subtrahend, the sum doesn't produce an n carry. Since, it's equal to 2 to the n minus m, right? So this is a 2's complement of n minus m. So here we perform a correction taking the 2's complement of the sum and placing the minus sign in front of the to obtain the result. Let's say minus n minus m inside the parentheses. Okay, these are the example of the steps we can use 2's complement for subtraction. So here we have one example, example 1, where we use 2's complement to subtract, right, unsigned number. So here, look, this is our minuend, m, this is n according to our notation, right? So in order to perform this subtraction, we use 2's complement of the subtrahend n and add it to the minuend. So these are minuend, right? And these are subtrahend. What we do is, instead of subtraction, we take the 2's complement. 2's complement of this is equal to the following, right? 2's complement is equal to 1's complement plus 1. Then we obtain the following. Well, once we have the 2's complement, we can add the minuend to subtrahend. So if you perform this addition, 0 plus 1, 1, 0 plus 0, 0, 1, 1 is 1 zeros, and 1, 1 is another 1, 0, and then 1, 1, and we have 1 propagating, and will be 1, right? And then 0, 1, 1, 0, 0. And we'll have the following carry, and carry, which is equal to the 2 to the n. 2 to the n. Well, we can discard this n carry and then leave the result of the following result, okay, which is correct value of subtraction. In this case, what we observe is that the minuend is greater than subtrahend. So if we, let me just write m and then n, right? So in this case, m is greater than m. Therefore, we can discard this carry and obtain the following result. Right? And then now you know how to get the 2's complement very easily, right? So we said 1's complement plus 1. Or there is another alternative method that you can use. And also, this carry indicates we don't have to perform any kind of correction to the result. Here is another example using 2's complement for subtraction. In this case, we are given again two numbers, minuend and subtrahend. This is minuend, right? Subtrahend, and we can denote it m and then n, right? And in this specific case, we can see that m is less than n, right? Minuend is less than subtrahend. Well, in this case, we follow the same steps. First, takes a complement of the subtrahend, okay, 2's complement, and then perform addition. So if we add this m to the n, we see that the sum doesn't produce an n carry, it is 0. Well, since it is equal to the 2, let's say 2 to the n minus, okay, this one is equal to 2 to the n, which will be minus n minus m. And then 2's complement of n minus m. In this case, we need to perform correction. This is the result of the summation. Right? The correction. Correction is done by taking the 2's complement of the sum, of the following sum, and then placing, let's say, a minus sign in front. This is a minus sign. So this is the result, again, will be equal to the following. So 2's complement, right? Let me just quickly do it as an exercise. Okay, 1's complement, 0, 0, 0, 0, 1, 0, 0, 0, plus 1, right? Then we get the 2's complement. Yeah, this is what we have. And then we need to append the minus sign in front. Look, in this case, although we are dealing with unsigned numbers, right, there is no way to get an unsigned result from this step. When working, let's say, with summation with a pen and paper, we can recognize the absence of this n carry. That implies the final answer must be changed to a negative number by appending negative, right? However, if this negative or minus sign for the result needs to be saved or preserved somewhere, it must be stored separately from the corrected n-bit result. Separately, right? Corrected n-bit result. Recall that signed integers are numbers with a plus or minus sign. Okay, that's how it's called signed integer. If we store n bits, okay, to represent a signed binary integer number, then out of n bits, n digits, right, 1 will be used to represent the sign of the number. And then the rest, let's say n minus 1 bit, will be utilized to represent the magnitude part of the number itself. For instance, the positive numbers, okay, and then 0 can be represented by unsigned n digit, okay, with radix r numbers. Then we need a representation for negative numbers. And to represent a sign, say plus or minus, we need exactly one more bit of information. One binary digit gives us 2 elements, which is exactly what we needed. The location of the sign bit is usually the most significant bit. in this example represented by as S. And then we have the remaining n, let's say -1 bit to represent the binary number, integer number. Here, S could take the value of 0 for positive numbers and value of 1 for negative numbers. Okay, this is sign. And here we have a index to represent the magnitude of in some form. Actually, there are various ways of representing signed numbers. Okay, some of them are called as one way is to represent signed integer is called sign and magnitude. Okay, another one is called through complements, signed complement, through 1's complement, through 2's complement. The simplest way of representing a signed number is this method, the sign magnitude method. Okay, here n-1 digits are interpreted as positive magnitude, while the sign, the most significant bit, will represent 0 or 1, denoting negative or positive number. In fact, sign magnitude, okay, binary format is the simplest format conceptually. In this method of representing signed numbers, as I said, the most significant digit takes, okay, the value of plus or minus. If the most significant bit in this case is 0, we can evaluate the number just as we would any normal unsigned integer. Okay, and also we can treat the number as a positive one because 0 denotes the positive. If the most significant bit in signed magnitude representation is 1, this indicates that the number is negative. The other bits indicate the magnitude of the number in this case. However, note that when dealing with binary arithmetic operations, it is more convenient to use the complement of the negative numbers. Okay, so either 1's or 2's complement method. Here, if you take a look at the following example, okay, of signed integer representation for base 2, n is equal to 3 bits, right? This is the decimal representation of the number, positive number, and the negative numbers. The sign magnitude method uses, again, the most significant bit to denote whether the number is negative or positive. 0, 0, 0, all positive numbers. 1, 1, 1, 1, all negative, right, numbers. 1's complement uses the following encoding of the positive and then negative numbers. Similarly, 2's complement. Well, signed complement forms of binary numbers can either use 1's or 2's complement. And again, in these 1's complement and 2's complement of binary numbers are important because they allow the representation of negative numbers. In particular, the method of 2's complement arithmetic is commonly used in our microcontrollers to handle negative numbers. Also, looking at this list, we notice that there is some peculiarity that there are two zeros. Right? One is positive, another is negative. And in sign magnitude, it is encoded by the following 0, 0, 0, 1, 0, 0. Well, this kind of encoding can cause problems for microcontrollers when checking the numbers, if they're equal or not. Another problem here is that performing additional subtraction is difficult, as it requires a special consideration of both signs of the numbers to properly compute the subtraction addition operation. Well, because of these kind of problems, sign magnitude method is rarely used for representing integers. Okay, more common ways are 2's complement. Now, using 2's complement addition, it is possible to design adder-subtractor circuit. Well, in this case, as we have seen in the previous examples, we can use 2's complement method for subtraction, which is obtained using the 2-step. First, complement each bit of a given number through 1's complement, and then add 1 to the result. Here we have the example circuit, okay, that computes either addition or subtraction for 4-bit, okay, number, binary number. So we see that these are full adders interconnected in cascade, 4-bit full adder, right? And then we have additional exclusive OR gates, 4 exclusive OR gates. And this is the carry in, which propagates. This is ripples, right? Ripple 4-bit adder. And then these carry out. What we have here is the sums, right? Output of the addition or subtraction between 2 bits. Depending here on the, let's say, value of the CS, S, right? This S. This circuit changes between adder or subtractor. For instance, if S is 1, then, okay, the circuit will subtract using 2's complement. Right? This 2's complement is formed at the output of this exclusive OR. This is basically 1's complement, right? And then 2's complement, we need to add 1. So 1's complement plus 1. The plus 1 is achieved, and adding the 1 to the result is achieved using this carry in, C0. If S is 0, then the circuit functions as adder, right? So this circuit is simple, much simpler, and doesn't require separate adder-subtractor circuit, right? So look, the importance of 2's complement or complement technique for building such circuit is here visible here, right? We can obtain a simpler circuit.